How high can water rockets go? Launching physics into the sky. Imagine standing in an open field on a sunny afternoon, holding an ordinary plastic soda bottle that you've just transformed into a sleek little rocket. You pump in a bit of air, step back, and that bottle shoots sky high, leaving a misty trail and a chorus of amazed cheers behind it. In that single burst, you can feel Newton's laws, fluid pressure, and the thrill of experimentation come alive. Today we're going to build, launch, and understand a water rocket together, turning a few household scraps into a fantastic lesson in hands-on physics. First, let's satisfy our curiosity about what makes a water rocket fly. A rocket engine, whether it's a huge Saturn V, or our humble bottle, works by pushing mass in one direction, so the rocket moves the other way. With big rockets, the mass is flaming exhaust. With ours, it's a blast of water and compressed air. The instant that stopper pops free, the pressurized mixture races downward, and Newton's third law answers with an equal and opposite push that sends the bottle upward. Simple, powerful, and very, very fun. Before we get messy, gather your materials. A 1 or 2 liter plastic soda bottle, a sturdy rubber stopper or sports ball inflation needle that fits the bottle's neck, a bicycle, floor pump with a pressure gauge, some duct tape, stiff cardboard, or thin plastic for fins, modeling clay or blue tack for nose cone ballast water, and a wide open outdoor space. Safety goggles and grown-up supervision are essential, because compressed air can pack a surprising punch. You might notice there's no fancy lab gear on that list. That's the beauty of this project science. Learning doesn't need to be complicated. It just needs thoughtful steps and a spirit of exploration. Let's start by preparing the bottle. Peel off any labels so you have a clear view of the water level later. Rinse the inside and make sure it's completely empty of fizz. Now decide which end will be the top. Most people leave the original bottle mouth at the bottom, because a strong, pre-molded plastic rim handles pressure well. If you prefer a proper nose cone shape, you can cut an extra bottle and tape its curved shoulder onto the base end of your rocket. Either way, the part that holds pressure threaded neck stays untouched. Next, come the fins. A rocket needs stability so it flies straight rather than tumbling. Cut 3 or 4 identical triangular fins from stiff cardboard or thin plastic. They should extend about 1/3 of the bottle's height and be evenly spaced around the lower half. Use duct tape to secure each fin. Press the tape firmly to keep air from sneaking under and ripping it off mid-flight. Don't worry if they are not perfectly symmetrical. Part of the fun is seeing how small design changes affect the trajectory, curved edges, extra wide flares. Try them and compare. Time for the nose. Without something up front, the rocket's heaviest part might be the tail, and that leads to unpredictable air. Mold a small lump of clay or blue tack and press it into the top tip. You've just added ballast, nudging the center of mass forward, so the rocket keeps its nose into the wind. Many kids decorate the clay with a paper cone for style points. Go ahead and make it colorful. Nothing in physics says science learning can't be beautiful. Now we build the launch system. Push a rubber stopper or inflation needle snugly into the bottle mouth. If you're using a stopper, drill a small hole through it to accept the needle of your floor pump. You want an airtight seal, no hissing during pressurization. If you're using a sports ball needle alone, wrap plumber's tape or rubber bands around the threads so it fits tightly. The key is holding pressure until the moment you deliberately release it. Let's load the Fill the bottle, roughly 1/3 with water. Why not fill it all the way? Because you need space for compressed air. Too much water means too little air for pressure. Too little water doesn't give enough reaction mass. Around 1/3 is the sweet spot. Insert the stopper assembly, make sure it's firm, then flip the rocket so the water sits near the stopper, and find a clear area free of trees, power lines, or curious pets. Place the rocket on a launch stand. A simple stand can be 3 sticks taped in a tripod or a wooden board with a drilled hole that holds the neck. Whatever you use, keep your face away from the nozzle, slip on safety goggles, and invite everyone to stand back at least 5 meters. Attach the bicycle pump hose to the needle. Begin pumping slowly, watching the gauge climb. You'll notice the bottle sides bulge slightly. That's the visual drum roll of pressure building inside. Around 40 to 60 pounds per square inch is common for a sturdy 2-liter bottle. But never push your luck or the plastic could burst. The real art here is listening. A faint creak, a subtle hiss, each telling you about the forces at play. Ready for blast? With one hand steadying the pump and the other controlling the launch, line maybe a quick release pin or simply a strong yank of the stopper with a long string countdown. 3. In a sudden, satisfying rush, the stopper pops free. Water gushes downward in a foaming plume, and the bottle leaps skyward. Take a moment to follow its arc. Did it rise straight? Did it spiral? How high did it go? Now the real learning starts. Tweaking variables. Try half as much water, then 2/3. Does more propellant mass beat higher air pressure? Add extra fins. Bend their trailing edges a little and see if spin stabilizes the rocket like a rifled barrel. Move the clay farther forward or back. Keep notes. This is your flight log, a treasure map of data pointing to better designs. Let's unpack the physics you're witnessing. When you pump up the bottle, you compress the air, storing potential energy. Releasing the stopper converts that potential energy into kinetic energy as water accelerates out, pushing the rocket upward. Newton's third law is the star here. Every action has an equal and opposite reaction. Meanwhile, Bernoulli's principle acts inside the nozzle of Fausta. The water flows. The lower the pressure at that exit, further hastening the rush. Gravity, of course, plays the opposing force, always tugging the rocket back down. Drag from air resistance chips away at upward velocity. That's why a smooth, streamlined shape extends flight time. And because the mass drops quickly as water empties, the rocket lightens during ascent, letting the remaining pressure accelerate it even more in the final milliseconds of thrust. There's an elegance in how these principles dance together. You can feel them each time you hear the thump of takeoff. Watch the arc against the sky and feel the splash of returning droplets. This isn't just a demonstration. It's a living textbook where the words are wind and water. Let's widen the lens. Professional engineers test serious launch vehicles in remarkably similar ways. They measure thrust curves, study center mass shifts, and refine fin geometry. Your backyard experiment echoes centuries of rocketry history, from ancient Chinese fire owls to liquid-fueled behemoths. By pumping a bottle, you tap into humanity's oldest dream, to leave the ground and touch the stars. Feeling adventurous? Try staging. Tape 2 bottles end to end with a simple coupler that releases the second when the first runs empty. Staging multiplies altitude dramatically, but it demands precise timing. Or experiment with camera payload. Just keep safety first and be mindful of local regulations about aerial objects. You might ask, could we make a bottle go into orbit? Sadly, its orbital speed needs around 7.8 kilometers per second, far beyond a plastic bottle's limits. Yet the principles remain the same, and every tweak you test teaches you a little more about the complex balance of forces that real rockets face. Before wrapping up, let's connect this fun to future careers. Aerospace engineers, meteorologists, and even amusement park designers use these same equations daily. By exploring water rockets, you're practicing skills that could launch satellites, improve weather forecasting, or create the next thrilling ride. That's the magic of STEM. Learning it turns play into possibility. So, what did we learn today? We turned everyday objects into a dynamic laboratory, applied Newton's laws in real time, studied fluid dynamics, and collected meaningful data. All it took was curiosity, patience, and a splash of water. If you remember nothing else, hold on to this. Science isn't confined to textbooks. It lives in the world around you and leaps skyward every time you ask, what happens if? Now it's your turn. Grab a bottle, gather some friends, and put your ideas to the test. Will your rocket soar higher than ours? Could you design fins shaped like eagle feathers? Or maybe add a parachute for a graceful descent? Tell us all about your trials, triumphs, and hilarious misfires in the comments. If this experiment lit a spark of wonder, tap the like button so others can join the adventure. Subscribe for more friendly explorations into the secrets of motion, energy, and the universe. And share the video with a fellow tinkerer who loves hands-on physics as much as we do. Until next launch day, keep your goggles on, your pumps ready, and your imagination in orbit. Stay curious, stay safe, and never stop exploring. Keywords: hands-on physics, science, experiment, STEM learning.